So my name is Mariza and Georgescu. I teach Introduction to Geology as a course for non-major students, Geological History of Life. When you say Geological History of Life, you immediately get into one of the most interesting problems in science, which is the theory of evolution. The interaction with the students in these courses, strangely, doesn't start from me, because the topic is so interesting. Usually, students interrupt me as I teach and jump with the questions. So the interaction with non-major students is much easier than with the major students, namely those who follow the stream of geology. I like to have discussions in the front of the other students with students in social sciences. Why? Because you see, evolution deals with large masses of organisms. And at some point, these organisms behave quite close to large masses of humans. Geology itself can be broken in more than 30 distinct natural sciences. Paleontology, one of them. Now, paleontology can be broken into 6 distinct sciences. One of them is micropaleontology. So, the paleontology of microscopical organisms. That is my field. Now, that field, the 6th part of the 30th part, can be broken in 42 large specialties. And one of them is broken in about 20 sub-specialties. So that's my specialty. I attended the Faculty of Geology at the University of Bucharest. I was a passionate guy already. So all I wanted to do is to study paleontology and theory of evolution. So at 18 years old, I knew exactly what I wanted to do in my life. I realized after I completed the university studies, I have to go in the oil industry and I need the experience. Forget about library, forget about discussions with the profs. I need to go there and study by myself, because this is how you get novelties in geology. When you study your own samples, you look at your own rocks, look at your own cores extracted from the bottom of the sea. So I needed that. Geology and paleontology and micropaleontology, where I'm specialist, these are sciences which permanently bring something new to you. You don't get bored. Truly, you always are under a massive informational bombardment of new things, novelties that require study. But then you realize, oh my God, but my life is so short. What can I do? All we can do is to hope that the next generations will do the right thing. But permanently in my career, I was challenged by these things. If I teach a course for non-major students, up to the first midterm, I take it very easy. I work and present the concepts at a very slow pace, just to make sure that we establish the avenues of communication. After that, I increase the pace, and at the end, we almost run. The student feedback is absolutely fabulous. I mean, they say, look, you can do very well in this course if you learn, if you read the textbook, if you attend the lectures and so on. Now, for the major students, well, the approach is completely different. Over here, we hit the ground running. What is the difference between me and the students at the beginning of their career, so to speak? I have more knowledge and I have more experience. 4 years in the future, they will be my competitors. So I want to have a good competition. I don't want to speak 4 years after with a student, a graduate, who doesn't tell me anything new about my profession. I want to see them thinking. I want to see them coming with their own interpretations, because this is how the world advances. Over here, I would say one very important skill a geologist must have, a paleontologist must have, is this: to take the right decisions and make the right interpretations, having very few data at our disposal. Geology and paleontology take every field, and you will see that everywhere there are patterns in the distributions of rocks and minerals, coals, hydrocarbons such as oil and natural gas, or different types of fossils. And there are patterns, and those patterns are governed not by one variable, but hundreds of them. So when we go in the field, we know something about the geological setting there, we know something about the history from the previous studies, but there is so much unknown ahead. Many students come with a very strong religious education. My purpose is not to destroy that. You see, science and religion were not considered antagonistic, as a lot of people consider today, until around the middle part of the 19th century, when some guys realized that they can have a very high prestige if these two, science and religion, fight. So now, 170 years after that, with the internet, which spreads information, some of it of very good quality, some of it not of good quality, the challenges are different. I teach the students that the age of the Earth is around 4.6 billion years. I teach the students that there is no planet which was formed first ahead of the others, or before the sun, or before the moon. No. All of them formed at the same time. I teach the students that life emerged on Earth from inorganic substances about 4 billion years ago. These come in contradiction with religious perspectives. But the story is, what are the differences? You see, the nature of science is this. I look at a rock, I make observations and draw the conclusions, make an interpretation, formulate a hypothesis. Now in religion, you look at the same rock, you have the same brain, but between data, observation, and my interpretations, there is a filter given by a holy book, which science doesn't accept. And this is my message to the students. Science and religion can work hand in hand. A person can be equally a formidable religious person and a great scientist, even in the theory of evolution. But keep them separate. Make sure you know what are you talking about and what you are doing. You make a scientific study, you don't put a holy book there. You are in religion, you use the holy book any way you want. I'm not a religious person, but in this way, truly you see that there is no trespassing between science and religion. When you think at the Earth rather as to a planet, but what happens after that? And this is how I teach it. I present the Earth as a planet, how it was formed, the Big Bang theory, and I end up with the Earth as a globe of molten matter. And then I say to the students, now let's change the scale. And we will look at it now from the building blocks of the rocks, from the minerals, and you will see that if we add successively concepts and new materials, we'll get at the end to the structure of the Earth. A vast amount of knowledge about the Earth, but when you look at other planets, you see that we speak of the same minerals. Of course, the internal structure is different, but there are a lot of common features with the Earth. So our knowledge on the Earth are very useful, for example, on the Moon, are very useful on Mars, and will be useful everywhere. Let's put it this way. I'd like to think science develops continuously. In both courses I mentioned, this is one of the most important topic. Is one of the most important part of science I convey to the students. Why? Because if you read the some websites, they will tell you how flawed are our measurements of the age of our planet. But those guys don't know what they are talking about because they don't have a training in science. And students come in my courses, in the courses I teach, with a preconception that the age of the Earth is calculated after one mineral or after one fossil, which is completely wrong. In fact, the calculation of the age of our planet is a process which lasted more than 350 years, happened through scientific advances almost continuously for 350 years, and is permanently improving. So at first, we ordered the layers and the bodies of rocks according to their relative position. You can figure out that the oldest one is at the bottom of the succession, and younger layers occupy higher up positions in the succession. Now, with many similar principles, we ordered the layers and bodies of rocks of the whole Earth crust, or a large part of it, in what we call the relative geological timescale. As we developed that, at the beginning of the 20th century, first in France, was discovered the radioactive decay. And then less than 2 decades after, in Britain, we had the principle of measuring or calculating the age of certain minerals. It took no less than 70 or 80 years until we perfected a methodology to calculate the age of these minerals with enough precision. And after that, in the remaining 4 decades, practically we improved this methodology so much. It's incredible, down to an age of 100 million years. The margin of error is less than 5,000 years, which is a blink of an eye. And everything in less than 40 years. But on the overall, the whole process of calculating the age of the Earth, and by this I mean also the age of each rock, the age of each fossil, which can be inferred from the whole scale, lasted more than 350 years. It is a whole process. This is exactly how I teach in my courses. With the only difference is that I keep, the whole thing at a high energy level. As I like to tell the students, I tell them from the beginning, look, if you have something to say, say it now, because after that, Gangnam style, with the same energy from the beginning to the end. It's a joke,